Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to the graphs of polar equations and the general idea behind graphing polar curves. So most people will memorize the graphs of polar curves. However, there's quite a few of them, and it's better if you could just generate the graph of a polar curve rather than memorize the graph of a polar curve. So that's what this video is all about, is how do I graph polar curves? And what are polar curves? All that fun stuff. So we'll start with this paragraph up above. The graph of an equation in rectangular form can be thought of as a series of ordered pairs satisfying the equation, and those ordered pairs are connected together with lines. Along the same lines, the graph of a polar equation is a series of ordered pairs as well. But those ordered pairs, as we know, are of the form r comma theta instead of x comma y. But those points are still connected together with lines. The difference is that polar curves are fascinatingly complex and beautiful, yet simple in mathematical form. They are usually, if you have any type of curve that has like a circular pattern to it or something like that, polar representation is often the better representation for that function. So as an example, consider this equation. The square root of x squared plus y squared is equal to 3 times the tangent inverse of y over x. A few things that you need to note about the tangent inverse: it returns an angle. Also, that angle is generally restricted to be between negative pi over 2 and positive pi over 2. So converting this equation to polar form, I'm going to use the fact that we have some formulas we've learned in the past, specifically that in polars, r squared is equal to x squared plus y squared. That is, r is equal to the square root of x squared plus y squared. And tan theta is equal, well, maybe I should say it this way, the tangent of theta is equal to y over x. That is, theta is equal to the tangent inverse of y over x. Well, technically speaking, theta is unrestricted versus this equation where theta is somewhat restricted because it's between negative pi over 2 and positive pi over 2. But still, converting this equation to polar form, that square root of x squared plus y squared can be rewritten as just r. And that tangent inverse can be written as theta. That's it. Now, one thing I still need to mention here, again, is that the tangent inverse only returns angles between negative pi over 2 and positive pi over 2. So that's going to be a slight restriction on this curve. But let's go ahead and graph this curve by hand. I'll start by placing the pole in space here and then the polar axis. And I'm not bothering with a ruler here, mainly because you likely won't use one either, so why should I? Now, rather than starting at theta equals negative pi over 2, which is the lowest value, actually it won't even return negative pi over 2, but rather than getting close to negative pi over 2 and starting angles at that, I'm going to start at theta equals 0. So imagine that you're facing the direction of 0, r against theta. So if you're facing the direction of 0, radians that is, r by this equation would be 3 times 0, or 0. So I know my initial point with this curve is just 0, 0. And then as you increase that angle in radians, well, the radius r will increase as well. In fact, the radius r will just be whatever, 3 times whatever the angle is. So if the angle is 0.1 radians, r is 0.3. If the angle is pi over 6 radians, then the radius is 3 times pi over 6, or pi over 2 in length, and so on and so forth. So essentially what happens is that as we begin to turn through an angle here, I always tell my students, it's as if you're throwing stones in front of you. So as you turn through an angle, you're throwing a stone in front of you, in front of you, in front of you, in front of you. And as we finally turn through to face the angle of pi over 2, which is this angle right here, we're throwing a stone in front of us a distance of 3 times pi over 2. So these stones just get further and further away until they're that far away. So this curve, which I've plotted as a bunch of points, starts opening like that. Now, if theta was unrestricted, so let's just pretend for a moment that the tangent inverse wasn't involved. Let's just pretend that we were originally given r is equal to 3 theta, and that's it. Well, if that's the case, then as you continue to rotate around the circle, the distances will continue to get larger and larger and larger. Okay, so it looks like almost like a seashell. As the angles get larger, the distances away that you're kind of throwing rocks in front of you, if you can think of it that way, it gets further and further. Now, that is not how you would generally graph a polar equation if it was the case that r was equal to a trig function, which in general, that's what r is going to be a function, or it's going to equal. It's going to equal a trigonometric function like a sine or a cosine. But when you have a nice polar curve, like r is equal to just some number times theta, they all kind of look like this. They're very nice to graph out. But this is not how you would normally do it, because the normal way of doing it gets more complex. So since the polar coordinate system is based on angles, most polar curves involve trig functions. The basic idea behind graphing a polar curve is to decipher whether or not it can be written as r of theta is equal to some trig function. If it can be, then we've got a way to graph it I don't want to say pretty easily, but somewhat easily. If, on the other hand, the polar curve cannot be written in terms of trigonometric functions, you have to get more creative. Basically do what we did in the previous page, which was just plot out a few points and see if a pattern begins. So here's my how-to on how to graph a polar curve, as long as that polar curve is of the form r is equal to a times the sine, or r is equal to a times the cosine. And notice how I write this out. R is equal to a times the sine of b theta plus d. And I write it that way because that's the way you learn trig functions in trigonometry. You learn them to graph them as y is equal to a sine of bx plus c plus d. So I like to keep everything aligned as much as possible with what you've learned. So in this case, you could still say the period of this is 2 pi over b, the amplitude is a, the absolute value of it, the vertical shift would be d. So if you were graphing in the Cartesian coordinate system, that would be the case. But we're not graphing in the Cartesian coordinate system, we're graphing in the polar coordinate system. So the graph is going to look significantly different. Not just slightly, but significantly. So what if you were given a polar curve that equaled a sine of b theta plus d, or a times the cosine of b theta plus d? How would you graph that? The first thing I highly recommend doing is graphing its Cartesian coordinate counterpart. So if you were handed r is equal to a sine of b theta plus d, graph in the Cartesian coordinate system a sine of bx plus d. You know how to do that? We've been graphing trig functions for quite some time, so that should not be any difficulty for you at this point. And just note the y values there represent r. So instead of r, we're graphing y, and the x values represent theta. Instead of theta, we're we're graphing the x values. So then after you're done graphing in the Cartesian coordinate system, in a separate area, you're going to plot the pole and the polar axis. And then from that point forward, you're going to refer to your Cartesian graph, the y equals function of x, and you're going to use the corresponding y value to plot r comma theta on the polar graph. So in other words, you're going to start at x equals 0. Let's just go ahead and I'll show you a simple example. For example, if you're asked to graph r is equal to sine of theta in the polar coordinate system, the first thing that I highly recommend doing is graphing y equals sine of x in the Cartesian coordinate system. Y is equal to sine of x, or if you want to call it the rectangular coordinate system, you can call it that too. So I've graphed y equals sine of x in the rectangular coordinate system. There's 2 pi, there's 2 pi, and we have pi as well, and pi over 2. We also have 3 pi over 2. You don't have to label all these points, but I'm just showcasing what they are. And then what we would do is we'd plot a pole and the polar axis. Now remember, the polar axis is associated with theta being 0. So you're facing an angle of 0. And what we want to graph here is r is equal to sine of theta. Well, going back over here, remember our inputs for sine of x are supposedly angles. So if x were 0, in other words, the angle is 0, then our y value is 0. That is, if our input, our angle is 0, the radius is 0. So when I'm facing that direction, I basically don't have a radius at all. And then I go back to this curve and I say, well, okay, now suppose that we start increasing angles. Well, as you increase your angle, the radius or the y value increases as well, until you get to the angle of pi over 2 and your y value is 1. How does that transfer over to our polar graph? Well, it says as you turn through an angle of theta, the distance that you're going to graph, the blue curve, is going to start to grow or move away from you until you're facing an angle of pi over 2, where your graph should be, well, that was a terrible pi over 2, by the way. This is pi over 2. Until you're facing pi over 2 when the graph is 1 unit away, when the radius is 1. So you're looking at something like this. Oops, that is not exactly how it looks, but I'll do it like this. Just help myself here. So you're looking at something like this. Again, as you were turning, you're throwing rocks in front of you. You can kind of think of it that way. And the distances increase until they're 1 foot away from you or something like that. That's how you can kind of think of it. And then coming back here, as you continue to turn past the angle of pi over 2, now you're throwing rocks closer and closer to you until when you face an angle of pi, you're just dropping a rock at your feet. That's a good way to think about it. So again, as you turn, you're throwing rocks away from you, but they're getting closer and closer to you until when you're turned to the angle of pi, you drop a rock at your feet. So it kind of looks like this. Okay. And so this is the path of travel of your view and how far out you were throwing rocks, I guess. That's kind of how I don't know why I think of it that way, but that's what I think of it as. And then if you continue on the sine curve here, let's see, moving past the angle of pi, what does this mean? It means that you're throwing rocks behind you, a distance of whatever this red line distance is, all the way until they're a distance of 1 behind you. So again, as I continue turning past an angle of pi, so I start turning this way until I get to an angle of 3 pi over 2, I'm throwing rocks behind me. So again, when I'm facing, for example, this direction, I'm throwing a rock back here. When I'm facing this direction, I'm throwing a rock back here. When I'm facing this direction, I'm throwing a rock back here. And when I'm facing 3 pi over 2, I'm throwing a rock back 1 unit behind me. So essentially, it just starts retracing the curve. And that description would hold if I continued beyond there as well. Because if you continue beyond 3 pi over 2, you still throw rocks behind you. These are negative distances. So you're facing these angles in quadrant 4, yet these are the directions you're facing, these are the directions you're facing, these are the directions you're facing, yet you're throwing rocks behind you, and behind you, and behind you, and so on and so forth. So that's how I have always graphed polar curves, is just by graphing in the Cartesian coordinate system first, and then turning to the polar coordinate system and saying, well, how far am I throwing things in front or behind me as I turn through angles? And that's exactly what this description is, but it's not as robust as what I just said. One thing you should be aware of: the vast majority of polar functions are overly challenging to graph by hand. Well, that's very true. That's the same as rectangular coordinate or rectangular equations. A lot of them are hard to graph by hand as well. So we will only focus on graphing polar functions that are commonly encountered in calculus. The other ones, that there are an infinite number of them, that aren't encountered that often in calculus, we will reserve technology for that. But what we're going to do here is graph by hand all the ones that you would commonly see in calculus. And that will start with the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.